And
some animations and everything where you can learn from?
No animations. It's all basic, just sort of like use old school. It's a paper. It's black and white. They have a physics book too for the trig base, and it's really short. It's just like a condensed version of physics. I thought about using it as a textbook.
How many pages would you say that one was?
I don't know. It's probably tells you 312. I would say. I would guess 312.
It's a very specific
Right.
It says 312. Right?
Blank 312 pages.
Let's see. You want to minimize this? I don't know if we did this last question. Did we do this last question? I didn't have it written down here. Let's try it out. It's a pretty basic question. Hey Lauren, we're doing this last question. Don't forget when you're calculating the energy, you have to convert everything to SI units. So that whole micro business has to go away. Mm-hmm. -9, right? Nano looks a lot like 9, right? You just replace the A with an I and the O with an E, and then you got 9. Cal looks just like dog. All right, just a few more seconds. 2:20, I'll stop. I think that's everybody. 3, 6, 7, 8, 9, 10. All right, 2:25, Stefan. A is right. Let's see, what other answer y'all put? I guess if you put D, you just forgot the 1/2. Is that what you did?
Yeah.
Yeah, so don't forget with energy. It's on your equation sheet, but where'd it go? It's 1/2 CV squared. So if you didn't put in the half, you get this answer, but that's wrong. A is the right answer. If you didn't convert this to 3 times 10 to the minus 6, that is 1/2 3 times 10 to the minus 6 farads. If you didn't do that, you got this answer, which is also wrong, and then 10 volts squared. And that gives you A. All right. Pretty basic stuff. So on your test, like in the free response, when you have that big circuit, I might ask you just as a throw-in question, well, what's the energy on C3 or whatever? All right. Y'all feel fairly comfortable with the capacitor circuits, the big ones? Yeah, I think most of you are probably okay with it, but you still need to practice a little bit before the test, which is, next Friday. Next Friday, right. So you'll see, well, since we just have two, yes, 20, did we say it's 28? Yeah, the 28. Since we just have 2 chapters, and chapter 3 is a really short chapter, you'll have a capacitor circuit, you'll probably have questions about like the geometry of capacitors, like the physical geometry of a capacitor, a free response question. There's not a whole lot of information actually, so you're going to see a lot on capacitors. You might actually see two capacitor circuits, one sort of more complicated like we've been doing, and then one just a simpler circuit. Maybe a combination circuit, but a simpler combination circuit. Alrighty? Y'all can do that, okay? Like y'all can do that today probably and be sort of okay with it, right? Alright, good.
Like, when you have like the two circuits in series, how like the voltage you have to go between 6 and 6 because it's the same.
Mm-hmm.
When you're doing it's on the 6 volts, on that one.
Right. Whatever your voltage is on that particular capacitor, right. Right. Mm-hmm. But I mean, like I said, on the question, you would have already answered that part of the question, like we've been doing. All right, let's move on to this next chapter, which is on current and resistance. Much of what, if you're in lab, I know a couple of you aren't in lab, but if you're in lab, you've probably already done much of this chapter, so that's a good thing. And we'll do it again here. Completion.
More practice.
More practice. And again, if you're looking at the old test, which I recommend, that chapter 2, have that question distribution, but chapter 2 included voltages and potential and all that stuff, as well as capacitance. So those are two separate chapters, and you can you just look for questions about capacitors. That's what you should be looking for. Is that clear? What's that? Right. I mean, we've already covered the potential difference, electric fields, all that business. But that's going to be on exam 1 for most of the previous semesters. But capacitors will also be on exam 1, so you need to draw those distinctions yourself. I'm not going to amend that. And by the way, if you're, some of you, there is this OpenStax book on the website. So if you go here, OpenStax, this is really a trig-based book, but it's a pretty good book out of Rice. And if you go onto this book, it's chapter 19 that covers capacitors. So if you want to just find a textbook that does a pretty good treatment of capacitors, it's chapter 19 in this book. Has anybody used this book at all? Looked at it for reference?
Well, we did it in class.
We did?
I mean, class.
Right, when we did that section on statics. All right. So let's look at current resistance. All right, so current is the rate at which charge flows past a point, at which charge flows past a point. In a given time. So like if I have you can think of it as water. We'll talk about it in terms of water. But if I have, water flowing through this pipe, or you can think of it as charge flowing past this pipe, I will, that's an I. I will watch right here and ask how many charges pass that point in a given amount of time. In this case, we're looking at a second. And so the current then is defined as just Q divided by T. Right, Q divided by T. How many coulombs of charge pass the point in a given time. And then the units are going to be the units for charge, which is coulombs, and the SI unit for time, which of course is second. So 1 coulomb per second is the equivalent to 1 amp, or ampere. It has an accent somewhere. Here, or maybe here, or maybe both. I'm not sure.
Or maybe right here. Well,
I don't know where the accent is. But usually when we abbreviate it either with a capital A or as what? Amp, right? AMP. All right, so these are the more common abbreviations. I'll use this one. I think that's the one y'all used in lab.
2 axes.
I don't know. It's French. I don't know. I have no idea. That's French, because you know most of our units come out of France, right? That's where the SI system is housed, in France. I don't know why that is, but it's just the way it is. Okay, we sort of talked about this conventional direction of current. Do you remember the fellow that sort of laid the groundwork for basically most of what we know about electricity today, at least in DC circuits? Who was that fellow? I'm a portly guy, bald, long hair.
Smart guy. Vinci?
No, not Da Vinci. He was American. Ben Franklin, yeah. So, Benjamin Franklin.
Just named like 50 people.
What were you
You
thinking?
know how many guys fit that description?
What was
That
that?
almost fits that.
I said, you know how many people fit that description you just gave?
Okay, lived in the 1700s.
Oh, you know that.
Okay, Ben Franklin. Yeah, was he 1780s?
Or 60 man.
I don't know, 1700 something, yeah.
No, if he said he was very, very old, then I would have got it.
All right, Ben Franklin. So he thought that the direction of current was, or that when you had direct current, there were protons that flowed in the circuit. And so he defined the direction of current based on the direction that protons would flow. And so if we're looking at a circuit like this, the protons would flow in this direction. So if I had protons flowing, they would flow in that direction. And so that's also going to be the direction of my current. If you remember back when we were talking about potentials, we set up two plates. One was positive, one was negative. This was our high potential, this was our low potential. And we said that protons, or positive charges, move from high to low potential. So in a similar way, that's what he said, is that our protons are going to move from high to low potential, and that's going to be in this direction. Because this is our high potential, this is our low potential. They're going to move away from the high and move around to get back to the low potential side. All right. So on the battery, you can think of this as our high potential and a low potential. Or I like to think of it as the high energy and low energy. Because remember, potential is just a measure of what for what. Y'all recall the basic idea of potential? This is one of those basic facts that I want you to walk away with from this course. Potential is what for what? Something per charge. Energy per charge, right? Potential is energy per charge. How much energy per unit charge do you give an object? Okay, so the conventional direction of current is the direction that a proton would flow. Electrons, by the way, the actual direction of current is going to be in this direction, because electrons move from low to high potential. So the actual direction of current is like that, but we're going to use the conventional direction, and that's standard for dealing with circuits. All right, you with me on this? This seems irrelevant right now, but it comes up a little bit later when we talk about multi-loop circuits in the next chapter. Okay, so you can think about also in this circuit, this isn't really correct physically, but you can think about that positive charges are repelled from the positive terminal. They're not really repelled, but you can think of it in that way, and they're attracted to the negative terminal. If that just helps you remember what is the conventional direction of current, and that's fine. Right, because positive charges repel one another, negative charges attract, or opposite charges attract, rather. So if that helps you, then that's great. If not, that's fine too. Okay, in the lab, have y'all done the ammeter, voltmeter lab yet? Where you find the resistance of those devices and use them in a circuit? Yeah, okay. We're going to go over that a little bit here. So in a circuit, if you want to measure the current, you're going to use an ammeter. And the ammeter is hooked up. It can either be hooked up in series or it can be hooked up in parallel. And if you imagine that you have a pipe and we have water flowing through that pipe, we'll sort of use this water analogy with electricity because it works really well, actually. If I have water flowing through this pipe and I want to know the rate at which the water is flowing through the pipe, I'm just going to stick a device in here, inside the pipe, like a wheel or whatever that will turn, and it'll tell me how fast that water is going through the pipe, right? So that would be in series or parallel? That's going to be in series. So in a similar way, whenever I want to hook up an ammeter, I'm going to hook it up in series. All right, because I want to put it right into the stream of the current and figure out how much current is going through that wire. Now, going back to this pipe, what if I put in a wheel that was very difficult to turn and really constricted the flow of the water? How would that affect the flow of the water? Would it affect the flow of the water? Huh? Right, it would go down, right? It would actually impede the flow of the water. But that's not what you want to do. You want to be able to put something in there that's not going to affect the flow of water or electricity hardly at all. So then, for our ammeter, do we want a resistance that is big or small? Okay. We want a very, very small resistance. So the resistance of the ammeter is very, say 2 or 3 berries. I think it's just 2. Very, very small.
You can put an extra one.
You could put an extra one. Basically, the resistance of an ammeter is similar to the resistance of a wire. It's negligible. Can y'all give me just a minute? I'll be right back. Is that okay? Sorry, I should have done this before, but very squared is fine. I'll be right back. I'm just gonna grab it.
Yeah. Then I'll put infinity squared. We're going to get faster than me. We can do that just so an infinite amount of exponents. Probably. Problem is, my brother-in-law, he's doing math that is not harder, but stupid. It's like, he took an oxymoron and he made an equation out of it, proving it false. Yeah, it was kind of like that, except it was not specifically geometry. It was saying that the statement is false, but it's truly false because it was true because it's false. But it's true. It's like, this is bullshit. This is logic. We only get one of the answers.
I'm sure you're doing great.
All right, sorry about that. So this is an ammeter, and in that last lecture you talked about shunt resistors. Don't you like that word, shunt?
My wife?
Did my wife, did she like have y'all say the word shunt?
Shunt.
I always make my students say it. Just say it right here. Shunt.
Shunt.
It's a cool word. Try to use that word.
What does it mean?
Huh? I don't know exactly. It's the. Is it the voltmeter or the ammeter that the shunt resistor? I forget now.
What is shunt?
We didn't go over that.
Seriously.
Yeah, never.
Maybe y'all have done this lab. Y'all done this lab though, right? Where you measure this resistance.
Oh no, that's next.
Maybe y'all. Maybe that's next.
That's next.
Alright, I'll have to make y'all say that. Or y'all just like when she says shunt resistor. Shunt. Like the way it rolls off the tongue. Shunt. Anyway, so the ammeter has a resistor inside of it, and you can see that resistor right here. It's just this little coil of wire, all right? And so you'll talk about that resistor next week. It's called, I think this is called the shunt resistor. Maybe it's called the multiplier.
Okay, something really fun.
Shunt is your resistance.
Right, yeah. So you see a little coil of wire up there. It's on the top of that plastic case. That's your resistor inside the ammeter. It's a very, very, very small resistance. Basically just the same as a piece of wire. It's basically just a piece of wire.
It was really fun. We were doing our experiment yesterday, and our power supply decided to burn like 4 fuses.
Oh, yeah. All right.
Fuses.
Go on down from here. Now to measure the voltage in a circuit, we're going to use a voltmeter. Right. And with the voltmeter, we're going to hook it up, what do you think, series or parallel? Parallel. Y'all have done this. The reason we hook it up in parallel, because you remember resistors are, remember with capacitors, if capacitors were in parallel, they have the same what? They have the same voltage. That's going to be true for resistors as well. So resistors in parallel will have the same voltage. I'll go ahead and write that up here. Resistors in parallel have the same voltage. And so if I have a certain voltage across this resistor that I want to measure, I can just put my voltmeter, which also has a resistance, and it will measure that same voltage. Right. Those two devices, my voltmeter and this resistor across which I want to know the voltage or the potential difference, they will be the same because they're in parallel. And resistors in parallel have the same voltage. Now, we have a certain current flowing through this circuit. Notice that's the conventional direction of current off of the positive terminal of the battery. And this current comes up here, and at this point it splits into two pieces. I have I1 and I2. This is something that we'll get into later. This is called the Junction Rule. You'll see it in a little while in next chapter, but I'm going to go and write it up here because it sort of follows that I is equal to I1 plus I2. That if I have this current that comes up through here, it's going to split into two pieces. I can't just lose current, right? So the sum of these two currents has to equal this current. That's true for a water pipe too, right? We had that when we didn't do fluids last semester. But that's true for a water pipe as well, that when water comes in and it splits into two pipes, the sum of the water is leaving the two pipes has to equal the water going into the pipe, right? That's from the conservation of, you know, which law of conservation that is? Mass, the conservation of matter, or mass. Yeah. All right, so we want to minimize this current as much as possible. We want to make that as small as possible so that this current is virtually unchanged. All right, so when determining whether or not the resistance of the voltmeter is big or small, we want to make I1 as small as possible. So that I2 is unchanged. Anytime you're making measurements, and this is generally true for all measurements, you want to change the physical quantity as little as possible. And that can be very difficult, especially in circuits. All right, so the voltmeter should have a big or small resistance in order to achieve that. It should have a very large resistance, a very big resistance. So that way I get a very small current I1 going through there. This is the resistor here. Now the resistor looks small. It's a little blue resistor, but it actually has a very large resistance. Like, you know, the resistor that was in that ammeter had a resistor of something like milliohms. But the resistor in this, the little blue resistor that you see in the back, has a resistance of 10 or 20,000 ohms. So it's a full million times greater than the resistance of that ammeter. But otherwise, they're basically the same except for the layout, their layout. So there's a little bitty blue resistor, and even though it looks small, it has a very large or small resistance. It's a very large resistance, like a full million times greater than this one. Let's try this. We're all passing that around. Just to measure a voltage across a resistor, you connect it which way? Parallel, series, replace a resistor with the device, or depend on the circuit. The little blue resistor is really big resistor. A bit longer, 45, I'll stop. 5 more seconds. must be right. Yeah, that's right. So you can see similar questions, just multiple choice questions regarding how you hook up a voltmeter and ammeter and how the resistance of those two devices are and why they are that way, so that they change the circuit as little as possible. All right, which of these statements is always true? Oh, well, let's leave off D. I didn't realize this, but D is the same as B. So we'll just leave off D. I'm not saying that B is the right answer, but just leave off D. All right, just a few more seconds. I'll stop. Stop at 120. All right, B is correct. Or D, as it may have been. All right, that's good. Let me show you. So first of all, the current through an ammeter is small. Well, yeah, it could be small, but what if your current is actually big? Then you'd have a big, like the current that you're measuring is big. Then that's not necessarily true that the current through an ammeter is small. But
And that already gets rid to
huh?
that already gets rid that already the process of elimination you've already figured
Right.
out your answer.
Mm-hmm. And so option 4, the voltage across a voltmeter is small. Well, that could be true if you're measuring a small voltage, but if you're measuring a big voltage, it's going to be big. So that's not necessarily true. And so that gets rid of 1 and 4, which gets rid of this one, as well as this one, because that one had 1 in it. So it only leaves you with 2 and 3. Now, you might not have known this right off, because we haven't done Ohm's Law yet, but just by elimination, you can see that. Ohm's Law, which we'll get to soon, just says that V is equal to IR, where R is something we'll define next. R is the resistance. And we'll get to this soon, but resistance just describes how much does the device resist the flow of electricity. How much does it resist the flow of electricity? So they came up with this really clever name for it called resistance. Do you notice resistance? Like, people think about these things. It's like capacitance, right? That's like another word for what? Not capacitor, but more capacity. The capacity to store charge. Capacitance. Capacity. Yeah. All right. So we know that the voltmeter, for example, has a very large resistance, and if it has a large resistance, it's going to have a small current. And the ammeter has a very small resistance, and so if it has a small resistance, it's also going to have a small voltage for a given current. All right, but we'll see that with Ohm's Law, and you'll see that in that voltmeters ammeters lab as well, that you'll actually measure the current and the voltage across those devices and find out that they're very small. It's kind of a fun lab. Like, I'm telling you that it's fun, but then you're going to get in there and you're going to say, this lab sucks. He said it was going to be fun. But it's actually a really cool lab when you think about sort of the voltmeter and ammeter and how it works. But many students don't like it. But I like it. Okay?
It's pretty much your opinion that you're giving right now.
It's not an opinion, it's a fact. It's just that the students in the past, their opinion is not aligned with the truth, which is that that's a cool lab.
Sorry about this lab.
The voltmeters and ammeters lab. I think y'all did resistors in parallel and series last, right? Which is also an excellent lab, I think.
If you're not annoyed because all all of the fuses start blowing, the wires start blowing.
Well, I wasn't going to say this, but usually when the fuses blow, it's because you have a problem in your circuit and you're drawing too much current off of the power supply.
Well, then we're in lab, it's just meant to do. We set up all the different resistors.
Sometimes you have it right. It's just something that's
Sometimes
freaky.
you can smell them very
Sometimes if they're old too.
Sometimes if they're old.
Perhaps we didn't have good enough wires.
No, it's not. It's actually pretty easy, actually. I mean, the measurements are all easy. I think it's kind of difficult to understand the shunt and the multiplier resistance, which I'll talk about, I guess, tomorrow or whatever. Okay. So let's look at resistance and Ohm's Law. So Ohm's Law is sort of one of our basic laws that we'll use to deal with circuits, and electricians use this. Even like an electrician that works on your house, he'll use Ohm's Law quite a bit to think about the current and the voltage across particular devices. Okay, so the flow of charge, which we defined as current, the flow of charge is our current, is proportional to the voltage. That is just to say that the current is proportional to the voltage. If the voltage goes up, you're putting more energy into those electrons, and that causes them to flow at a faster rate. If a battery provides greater voltage, that's just what I said. If it provides greater voltage, it provides more energy to the electrons. Thus, there is a greater flow of charge. So I is proportional to our voltage, our potential difference. And Ohm's Law is going to describe the relationship between these. I'll give y'all just a minute before I go on to the next page. I tell y'all about our RV trip out west. We're going out west. We're flying to Phoenix, and then we're going to go to Flagstaff for a week for a conference, and then we're renting an RV. And we're going like all up around. We're going to Las Vegas for like a night and a day, and then we're going to Zion for a few days, Zion National Park, and then we're going to Grand Canyon, and then we're going to Page, Arizona, Lake Powell.
What is this?
It's next week. I'm going to take off. See y'all.
Bye.
No, it's this summer.
Last, like a month.
It's next summer. And then we're going to Grand Canyon, of course, for several days. And then we'll go to the Petrified Forest for a day and a half or so. And then we'll go back to Phoenix.
Is this phys202 right now?
Yeah. Well, I mean, for the 9 days, our RV is costing about $1,300, which isn't that bad. But and that includes miles, but it doesn't.
That includes miles?
Yeah, but it does not include gas, which is another cost.
That's really
Yeah, and then all those parks, they cost to get in. I mean it's going to be about a $4,000 vacation. But it's something we'll do once in our life. So people go to Disney World and spend a lot more than that.
Take your camera.
I think we'll get. I think so, Lauren. I've never been there, but yeah, I know. Yeah, I've seen pictures of it, and it's just this vast field of all these petrified trees. I mean, they're falling over and stuff, of course, and then there are a lot of petroglyphs too, I understand, from Native Americans.
If you go to Grand Island, you can probably find the forest of driftwood.
Right. Okay. I'm sorry. That was just a little brief advertisement. So if anybody wants to go with us, you can sleep with my little boy. Huh? Right. All right. So Ohm's Law describes this relationship, and Ohm's Law defines the resistance. It's equal to V over I. Sometimes we'll write Ohm's Law in a different way. I'll write it down here. We write it as V equals IR, and this is sort of the more common way. That might be the way it's written on your equation sheet, but usually when I write it, that's the way we'll write it. And we're going to sort of use this akin to that rule that we had with capacitors when we get later into circuits. Remember we had that rule Q equals CV? We're going to sort of think of it in the same way, though it's different, but we'll sort of use it in a similar way. All right, so for a material, if R is big, it requires a greater potential difference or a greater voltage. to cause a current. All right, look, I have a what do y'all think that is? It's a log. Thank you. It's a log.
Thank you.
Draw some bark on it. I have this log. You think it has a small resistance or a big resistance? Big resistance. It's an insulator, right? But I can put a current across there. If I put a big enough potential difference between this point and this point, eventually I'm going to get a current. It's going to vaporize it too, right? If I put a big enough voltage, it's just going to poof, burn up and it'll be gone. But if I put a big enough voltage, then it will cause a current. So if you have a big resistance, you require a big voltage in order to get a current. And that's fleshed out here in this relationship, that if I want a current in something that has a big resistance, I have to provide a big voltage. All right. Likewise, it's for something that has a small resistance, you just need a small voltage to cause a current. So like copper wire, for example, big or small resistance. Very small resistance. Don't need much energy to push electrons through copper wire. Very little energy at all. All right. The unit for resistance, anybody know? It's the ohm, right? The Greek letter omega. Ohms. I don't know where that comes from. You might know the history of that? I don't know. No, it wasn't that. I think it's some electrical engineer came up with it. All right. Let's try this quick test. Simple question. So I want to know what is the total charge that passes through the resistor in 2 minutes with 2 volts across a 10 ohm resistor. Yeah, remember your definitions. V is IR, I is Q over T.
Smell it all over my arms.
Sorry. Don't forget you need SI units on everything, folks. So some of these things aren't in SI units. All right, I'll stop at 225, or 228 rather. A few more seconds, just guess if you don't know. All right. See, I think that's right, let's just check it. So, simple question, I just want to know, first, I have to figure out what is the current. That's going to be V over R from Ohm's Law, just solving that for I. That's going to be 2 over 10, which is 0.2 amps. And then I go back to my definition of current, which is Q over T. And I'll find Q, which is the current times the time. Q is IT, that's 0.2 amps times 2 minutes, which is 120 seconds. Which is, so if you put C, you probably didn't convert that to minutes. And this is going to be 24 coulombs. All right, 24 coulombs of charge pass in 2 minutes for this sort of typical resistor. Simple circuit. All right. Let's look at one more thing, and then I have something I want y'all to do. I go down from here? Yeah, we're going to have nap time. And if you actually go to sleep, I'll give you a ticket. But if you're not going to sleep, just play possum, okay? That's what they tell them. Most of the kids don't sleep, right? So. Huh? Okay. Now, Ohm's law applies to most materials for which their resistance is constant over a wide range of V and I. We call these devices ohmic. And ohmic just means it follows Ohm's law. So if we were to plot I versus V, it would look like this. It would look like a straight line. Whenever you increase I in this direction, or V rather, I increases by the same amount. Right? Let's see. So I know that V is equal to IR. So if I rewrite this equation, I get I is equal to 1 over R times V. So what is the slope of this line represented by? I did this 2 labs ago. Huh? What is it? Right, so the slope of this line is equal to 1 over R. I should have done that in lab. R, if you plot V versus I, it'll look a little bit different. If I plot V versus I, the slope of that line is equal to what? Is equal to R. Okay, so that's ohmic devices, and they just follow Ohm's law. They're called ohmic devices. Now, for non-ohmic materials, and we're not going to get into non-ohmic materials really at all, just to recognize that they exist, the resistance of the material changes as the voltage and the current change. So, for example, you might have something like this. That's non-ohmic. When it reaches a certain potential, its resistance changes drastically. Or when it reaches a certain current, its resistance changes drastically. A diode. Yeah, so a diode is an example of that. If you look in a circuit, a diode looks like this. I think this is the symbol. It's a triangle. Yeah. We're not gonna deal with diodes, but you might see them in the future if you do any sort of instrumentation or whatever. But a diode is like a gateway for current. It only allows current to flow in one direction. So when you have current flowing in one direction, it acts ohmic, but when it's flowing in the opposite direction, it cuts it down. So its resistance just shoots way up, causing the current to not flow in that opposite direction. Right, so this is a diode. Diodes are just an example of a non-ohmic device. You have a small resistance in one direction, and then a very large resistance in the opposite direction, which means that current doesn't flow in the opposite direction. So let's try this quick test, and then we'll be sort of done. Given these values, is this device ohmic or non-ohmic? That is, does it follow Ohm's law, or does it not follow Ohm's law? So another way of thinking of this, for an ohmic device, the resistance should always be constant. It should never change, unlike for the diode where it does change. So does this resistance change? stopped at 115. 115. I'll give you to 120. 120. A few more seconds. B is right. Very good. So a simple way to look at this is just ask yourself, what is the resistance? R is V over I. So in the first case, it's 3 over 2, or 1/2. And in the second case, it's 6 over 3, which is equal to 2. So my resistance is changing for this device, so it has to be a non-ohmic device. All right. I just want you to know that these exist, ohmic versus non-ohmic devices. All right. We are going to finish Chapter 3 probably next time. And on Monday, we'll move, actually, we might move on to Chapter 4 next time. But Chapter 4 will not be on the exam. It'll just be Chapter 2B and Chapter 3. Right now, I want you to take out a blank sheet of paper. And as you know, if you've had me before, I like to do midterm assessments. I think that a course should always be changing to meet your needs. So I want to know two things. One thing that you like about the course, and then one thing that you'd change. And if it's within my ability to change it, I will. So one thing that you like, and one thing that you would change. Right, one thing you like, one thing you hate. You don't need to write your name on it. Then you can go. You can just lay it right here, face down. One thing you like in a sentence or two, one thing you like, and one thing you change.